All right, welcome to the deep dive. If you're here with us today, it's because you really want to grasp what's making waves in the tech world. And today, we're diving deep, no pun intended, into silicon carbide, or SiC, as you'll hear us call it.
Yeah, I mean, you keep hearing about it, Silicon Carbide, six the second that, but it's not just hype. It's really becoming a game changer for a lot of things, especially sustainable energy and those high power applications, all the stuff behind our modern infrastructure.
Yeah, and actually the source material we're using for this deep dive really gets into the specifics of that, doesn't it?
Yeah, it does.
SiC cell crystal growth and wafer processing.
Yeah.
It's by Dr. Deepak from Orbit and Skyline. And Orbit and Skyline, they specialize in, well, semiconductor fab solutions and OEM services.
Right.
But with a real focus on SiC cell processing.
Yeah, they're really in the thick of it. I mean, what's so interesting about this overview is it doesn't just look at what we get at the end of the process. It really digs into, how do we even make this stuff? And I think that's what we're going to try to do today.
Yeah, exactly. We're gonna pull out the key knowledge about why is SiC so important right now, what makes it so difficult to actually make, and what are some of the innovations that are, pushing its capabilities forward.
Definitely.
So why is SiC so crucial these days? Why is everyone talking about it?
Well, the overview lays out pretty clearly why SiC is becoming, the go-to in a lot of high-power applications. It really comes down to, its basic material properties. So, for example, it's got this band gap that's 3 times wider than silicon, and it has a much higher critical electric field.
And what does that mean for someone, like our listeners who are following the industry? What does that mean in practice?
That means in practice, it can handle a lot more voltage before it breaks down. So, if you think about silicon-based IGBTs, SiC can operate at much higher breakdown voltages, and on top of that, it's got amazing thermal conductivity.
Right.
And that just means it can dissipate heat way better.
Which, of course, in high-power electronics, that's a huge deal.
Totally. And that means you can potentially get rid of those, big clunky cooling systems. And this is where companies like Orbit and Skyline, with their specialized semiconductor fab services, really come in because you need that level of precision when you're working with this kind of material.
Now, the overview mentions over 250 different polytypes of SAR.
Yeah.
That sounds like a lot of variation. Why is that so important?
It is a lot. I mean, essentially, these polytypes, they're just different ways that the atoms arrange themselves in the SiC crystal lattice. And because they're arranged differently, they each have their own slightly different electrical characteristics. The overview really hones in on 3 of them. There's 4H, 6H, and 3C. And while the different polytypes, they could be optimized for certain uses, the industry is really zeroing in on that 4H polytype because it's just got great all-around performance for power devices.
So why is the 4H structure so much better, so much more advantageous?
Well, the 4H structure, it really has kind of this sweet spot of properties. Like it's got high electron mobility, which is key for those fast switching speeds in power devices. Plus, it's got that high breakdown voltage we talked about, and it's still got that excellent thermal conductivity. So this makes SiC, not just competitive with silicon, but often better.
Right.
And Orbit and Skyline, they actually touch on this in their blog post, Silicon Carbide, the future of the compound semiconductor industry.
Okay, so it's got the right stuff.
Yeah.
But the overview also goes into detail about just how hard it is to actually grow those silicon crystals into those larger wafer sizes, like 6-inch wafers, and now they want to get 8-inch wafers.
Right.
What are the biggest challenges in actually making these wafers?
That's a major challenge. Growing these big, high-quality single crystal wafers, it's not easy. I mean, first off, you need these insanely high temperatures, like over 2,000 degrees Celsius.
Wow.
And then the crystal growth rates are super slow. You're talking like 0.5 to 2 millimeters per hour. Plus, inevitably, you're going to get these crystal defects, micro pipes, stacking faults, high dislocation densities. And these can really mess with the performance and reliability of the devices you're making.
So it sounds like that would really affect how many wafers you can actually produce that are good. So why are they so focused on getting these larger 8-inch wafers?
It really comes down to economics. So even though an 8-inch wafer might cost about the same to make as a 6-inch wafer, you can fit way more devices on that bigger surface area.
Right.
And that just means you get a higher yield, more devices per wafer. And that translates to a lower cost per device. And that's huge for making this technology, widely adopted.
Okay, so bigger wafers are the goal, even with the added complexity. Now, the overview talks about physical vapor transport, or PVT, as the main way to grow these crystals. What makes PVT the technique of choice?
Well, unlike silicon, it's stoichiometric cyclia, so that's a perfect one-to-one ratio of silicon to carbon. It doesn't actually exist as a liquid. Like it doesn't melt in that way. And to make things even trickier, carbon has really low solubility in molten silicon, and that basically rules out a lot of other methods they use to grow crystals, especially for that 4H polytype that we talked about, the one they want. And Figure 1.3 in the overview, it actually suggests that, for the high power devices that we're talking about, PVT just strikes that right balance between being able to scale up production and the rate at which you can actually grow the crystals. And companies like Orbit and Skyline, with their process engineering know-how, they're really working to tweak those growth processes to get better yields and fewer defects. And they even discuss this in their blog Silicon Carbide: Properties, Benefits, and Applications.
So PVT is the workhorse. Can you walk us through how it actually works? I mean, it sounds pretty complex.
Yeah, it is. It's actually pretty cool. So you start with the super pure SiC powder, and they put it in a special crucible inside a furnace, and they crank up the heat, like way up, over 2,000 degrees C. Now, at the top of the growth chamber, there's this really carefully cut piece of SiC single crystal, and it's called the seed crystal. So inside this, carefully controlled low-pressure environment, the SiC powder, it actually undergoes sublimation. It goes straight from a solid to a gas.
Right.
And these gaseous species, things like CSA2, Si2C, and atomic silicon, they all float up towards the seed crystal, which is kept a little bit cooler.
And is that where the new crystal actually starts to form?
Yep, exactly. So those vaporized CT species, they condense onto that seed crystal. And because that seed is a perfect single crystal, the new material that's deposited, it lines up perfectly with that existing structure. So essentially, you're growing this larger, high-quality single crystal just by very, very slowly depositing more material on top, all at those crazy high temperatures. And then after a while, and it can take a long time because those growth rates are so slow, you get this large crystal. It's called a boule. They very carefully take that boule out, and then that boule is used to make more seed crystals, which they use to grow even more boules. But to make those seed crystals, they got to do some really precise dicing and polishing.
Right. So the overview also mentions, the importance of doping, creating N-type and P-type semiconductors.
Mm-hmm.
How do they do that during this crystal growth, and why is it so important to have those different types?
So doping, that's all about controlling how well the semiconductor conducts electricity. And the overview points out that N-type doping in SiC, which is usually done by adding nitrogen gas during that PVT process, that's becoming really popular because it's more scalable and they can get a wider range of doping concentrations. And what's interesting is that adding nitrogen actually helps to stabilize that 4H polytype that everyone wants.
Oh, yeah.
Because it kind of creates these carbon-rich regions within the crystal, and those carbon atoms, they fill in these gaps, promoting that N-type conductivity. Now, if you use aluminum as a P-type dopant, it actually tends to favor the 6H Cali type, which makes it harder to consistently get that 4H structure.
Yeah.
And then there's also this idea of semi-insulating substrates, which the overview mentions as well.
Yeah. And what's the point of those? What role do they play?
So semi-insulating substrates, they're basically highly resistive. And they're really important for specific high-performance applications, especially in those really high-frequency electronics, like what they're envisioning for 6G technology or in these super high-speed data transmission lines. And this high resistivity, which you can get either through the natural point defects in the SiC, that's called HPSI, high-purity semi-insulating acidic,
Right.
or by adding vanadium during growth. What that does is it minimizes this unwanted electrical coupling, it's called crosstalk, between different parts of the circuit. And that isolation is really important to keep the signals clean, especially at these really, really high frequencies.
So now you've got this impressive crystal. The structure is right. The doping's controlled. But the overview emphasizes purity. Why is that such a critical factor?
Oh, it's huge. So the quality and the performance of the 6 spool, it's very dependent on how pure your starting 6 powder is, and also how pure the graphite components are in that high temperature furnace. I mean, even tiny, tiny amounts of these unwanted elements, like the overview lists, titanium, vanadium, chromium, iron, cobalt, nickel, sulfur, even a little bit of these can really mess up the electrical and structural properties of the crystal. And that can lead to defects and just overall worse performance.
How do they even detect those tiny little bits of contamination? The overview mentioned something about the color of the 6E wafers.
Yeah, that's right. So the color of the SiC wafer, it can actually tell you something about what kind of dopants and impurities are in there. Because these different elements, they change the electronic structure of the material, which then affects how it absorbs and transmits light. And the overview actually gives a table that shows like the typical colors you'd see for high purity N-type and P-type Ca across the 3C, 4H, and 6H polytypes. For example, like high purity 4H Ca is usually colorless, while the N-type material might look kind of amber and the P-type might have a blue tint. So it's kind of like a quick visual check during quality control.
Okay, so you have this carefully grown bull, a little impure maybe.
Right.
What are the next steps in turning this into usable wafers?
So here's where the hardness of SiC really becomes a pain. SiC it's super hard. It's like 9 to 9.5 on the Mohs scale. And while that hardness is great for high power applications because of that high critical electric field strength, it makes processing this thing incredibly difficult, especially when you're trying to slice it into these really thin wafers.
Yeah, trying to cut something that hard, it sounds like a feat. So what's the first step after they've grown the bull?
Well, the first thing is they got to shape it and size it, because when it comes out of the furnace, it usually has a kind of irregular shape. So they have to center it and mount it on this special lathe or grinding system to get it lined up just right with its crystal axis. And then they use these super hard diamond abrasives. I mean, that's really the only thing hard enough to actually cut city. And they grind away the outer layers until they get this perfect cylindrical shape, and they have to get the diameter just right to these very tight tolerances. And then they do this really careful finishing process to smooth out the surface and get rid of any stress. Because if there's any stress in there, it can cause problems when they slice it into wafers.
Right.
And companies like Orbit and Skyline, they're really at the forefront of this. They're providing the equipment engineering services to help overcome these industry challenges.
Right. So the boule is now the right shape and size. So now it's time for the really delicate part, slicing it into those thin wafers.
Yeah.
How do they even do that without shattering the whole thing?
Well, this is where they use these really fancy multi-wire saws. And these aren't your regular saws. They use a bunch of very thin wires that are coated with this diamond slurry. And by carefully controlling how fast the wires move, how much tension is on them, and even the size of the diamond particles, they can slowly slice the boule into these wafers with minimal material loss that's called kerf loss. And these new sawing techniques, they're not only really precise, they also let them process more boule quickly, and the quality of the wafers is just much better, both in terms of the surface finish and how uniform the thickness is.
So after they're sliced, those wafers are still pretty rough, right? What's the next step in smoothing them out?
Yeah, you're right. Slicing leaves behind some bumps and dips. So that's where they do lapping. And lapping basically involves putting the wafers between these rotating plates with a special abrasive slurry. The slurry has these tiny abrasive particles that gently grind the surface of the wafer until it's flat, and the thickness is uniform across the whole wafer. And it's tricky because they got to remove enough material to make it flat, but they can't overdo it and ruin the surface for the next step, which is epitaxial growth.
Right. And that's where they grow additional layers on top.
Exactly.
So the final stage before they can actually start growing those layers is the EPI-ready polishing. Right?
Yeah.
What does that involve?
So the final polishing is called chemical mechanical polishing, or CMP. And this one, it's super high tech. It combines mechanical abrasion, so that's using really, really fine abrasive particles in a chemical slurry, with controlled etching of the CC surface. And the goal here is to get rid of any microscopic defects on the surface and make it atomically smooth. Yeah, I mean, that ultra-smooth surface is absolutely critical, because if you don't have that, you can't grow those high-quality epitaxial layers without introducing defects. And those defects can mess up the performance of the device. You know, things like carrier mobility and breakdown voltage.
CMP sounds essential, but the overview mentions that it could be a slow process for SiC because it's so hard. Are there any innovations that are trying to speed that up?
There are. So because Cirrus is so incredibly hard, it just takes longer to polish compared to silicon. But they've been developing these new rapid thinning techniques. And what they do is they use these special polishing pad materials and optimized diamond slurries, and that lets them get much higher material removal rates. The overview actually says they can get weights up to 1.5 micrometers per minute.
Wow.
While still getting that super smooth finish with roughness below 6 nanometers. So that increase in material removal rate, that really cuts down on the processing time and the costs.
Okay, so it seems like this whole process, going from that boule to the final polished wafer, it's incredibly detailed and time-consuming. And the overview stresses this idea of needing a single-stop solution.
Yeah.
Why is that so important for SiC's manufacturing?
So because it's so hard to process this material, having it go through all these different steps at different companies, it adds a lot of complexity and it increases the chance of things going wrong.
Right.
And a single-stop solution where everything happens under one roof, that can really streamline production, it can cut down on handling time, and it ultimately lowers the manufacturing cost. The overview also points out this problem, that there aren't really good defect characterization tools for the boulets when they're first grown.
Right.
So you might not know if there are problems with the crystal until you've already done a bunch of processing. And while they can do some analysis during the growth process, it's not perfect. So they're working on new technologies like this Bula Pro 200AX, which uses X-rays and UV lamps to check the crystal quality early on. Plus, there are these alternative processing methods, like the one that Purion AG is developing, which claims to be much cheaper than traditional grinding and thinning.
It's interesting that the overview mentions that a lot of power device companies are actually starting to set up their own foundries to do the Bula growth and wafer conversion themselves. Why are they doing that?
Well, it's mostly because buying synth wafers and all the other stuff you need from outside suppliers, it's just super expensive.
Right.
And plus, you're kind of at the mercy of the supplier's schedule and production capacity. So by doing it all in-house, they get more control over the whole process, it's more reliable, and they can actually save a lot of money. The overview says they can potentially reduce the die cost by like 25 to 40%.
Wow.
So it's a big deal.
Okay, so now you've got this high-quality polished Simmers wafer. But to make a lot of those power devices, you need to grow these additional thin layers and control the doping very precisely. And that's where epitaxial growth comes in. And the overview mentions that it's really hard to get that doping perfectly uniform throughout the boule when you're initially growing it.
That's right. It's super tricky.
So why is homoepitaxy so important? That's where they grow a layer of Simmers on top of an existing SimFreeze substrate.
Yeah, so homoepitaxy, it's all about that fine control. It lets you control the doping concentration and the thickness of the layer with a much higher degree of accuracy. And that's what you need to get those really specific electrical properties in the final device. Things like breakdown voltage and switching frequency.
And when it comes to the actual techniques they use for this epitaxial growth, high-temperature chemical vapor deposition, HTCVD, that seems to be the most popular one. Why is that?
The overview does mention a few other techniques, but yeah, there are other methods like molecular beam epitaxy, that's MBE, liquid phase epitaxy, or LPE, and sublimation epitaxy.
Right.
But HTCVD, it's the best combination of precision and scalability.
Right.
So like LPE, for example, it can have problems with impurities getting in, and it's harder to control the ratio of carbon to silicon, and it's not as easy to scale up to those larger wafer sizes. Sublimation epitaxy, that can be faster sometimes, but it's harder to control the background doping and make those really sharp p-in junctions. And then MBE, that one gives you incredible like atomic level control, but it's super slow and it's got its own challenges with the high temperatures. So HTCVD, it gives you that precise control over both the doping and the thickness that you really need for high-power SiC devices.
The overview even mentions this specific piece of equipment, the Extron G10 SiC model that they use for this HTCVD process.
Yeah.
What can that thing do? What makes it special?
So that Extron G10 site, that's like a state-of-the-art reactor that's specifically designed for growing these high-quality SiC epitaxial layers, and it lets you really fine-tune both the thickness and the doping. They usually use precursor gases like monosilane, that's AH4, as the silicon source, and then propane or ethylene as the carbon source. And they carefully mix these with carrier gases like hydrogen or argon. And these reactors are big. They can handle wafers up to 8 inches in diameter, so you can grow these nice uniform epitaxial layers across the whole wafer. The overview also points out that they usually do this growth on a specific crystal plane, the 0001 plane, and they got to be really careful with the process conditions, like keeping the carbon to silicon ratio just right. And before they even start growing the layer, they actually do this in situ cleaning step, usually with hydrogen chloride, gas, and hydrogen, just to make sure that the wafer surface is completely clean. And that's super important to get a nice high-quality epitaxial layer and minimize any defects.
Right. So we've really gone through the whole journey from those raw materials all the way to that finished wafer with all the layers. The overview in its conclusion really highlights some key advancements that have been made in SiC wafer production. What are some of the things that really stick out to you?
So the summary, it really brings together all the amazing progress they've made in every stage of the process. And one of the big things is this move from 6-inch wafers to 8-inch wafers.
Right.
Because that's really what's going to bring the cost down and make this technology more accessible.
Okay.
And at the same time, they're getting better and better at reducing the defects in those larger wafers, like those threading edge dislocations, the TEDs and basal plane dislocations, the BPDs. They're now getting densities down to 10 Chen in cm-Hess. And the way they slice the wafers is way more efficient now thanks to those diamond-coated wire saws.
Right.
They used to take like 16 to 20 hours to slice a boule. Now it's down to about 4 hours. And they have much better control over the thickness variation. Now it's less than 2 micrometers. And they're even moving towards these single-side lapping techniques, which give them more control over how flat the wafer is.
Right.
Although it can take a little bit longer. And the surface grinding, that's gotten a lot faster, too.
Okay.
Now it only takes like 5 to 10 minutes per wafer. And they hardly lose any wafers during that step, maybe 1 or 2 per batch.
And what about this push towards those even larger 200-millimeter wafers, 8-inch wafers? What are
Right.
the advantages there?
So those bigger wafers, the main thing is you can fit way more devices on them.
Right.
So they could potentially increase device yields by as much as 33% compared to the 150-millimeter, those 6-inch wafers.
Right.
And the other nice thing is that they might be able to reuse some of the older silicon fabrication facilities to handle SiC, which would save a lot of money.
Right.
But the overview also points out that SiC wafers are a lot thinner than silicon wafers, like almost half as thick. So they're going to have to adapt some of the equipment so they don't break the wafers.
Right.
And then there's also this issue of energy consumption. Growing those boules takes a ton of energy. I mean, the temperatures are over 2,000 degrees Celsius, and it uses thousands of kilowatt hours of electricity per boule.
Wow.
So it's really important that they start using renewable energy to make this whole process more sustainable and to bring down those long-term production costs.
So to sum it all up, CI is a really exciting technology, and it's crucial for things like sustainable energy and more efficient high-power electronics.
Yeah.
But as we've seen, going from that raw material to the final wafer it's a really complex process. It really shows the incredible innovation that's happening in materials science and engineering.
Yeah, definitely. And it's a process that's constantly being refined and improved. There's just so much research and development happening all across the supply chain.
So one last thing to think about. We talked about how energy intensive it is to make SiCs. So how will those future advances in renewable energy, how will that impact the environmental footprint of this material, but also its scalability and affordability? I mean,
Yeah.
It's really interesting how those things are connected.
It is. That's definitely something to keep an eye on as this technology matures. And for those of you who want to dive even deeper, I definitely recommend checking out the resources that Orbit and Skyline has.
Yeah, they have a lot of great information.
They really do. They go into a lot of